Hi folks. Today we're going to look at algebraic interpretations of limits. But before we get into that, we're going to look at one interesting limit, the limit as x goes to 0 of sine x over x. So clearly you can't just sub in 0, you get sine 0 over 0, or you'd end up with 0 over 0, which is weird. Let's take a look at the graph. From this graph, if we trace this with our fingers, it looks clear that the limit as x goes to 0 of sine x over x is going to be 1. It goes towards 1. But there's something really weird about this. If you actually go to 0 on this function, of course, it's not quite going to exist there. And you can see it's got a hole. It says 0 undefined. That's about the actual point that we're talking, right? But the limit is what we approach, so it's going to be 1. Now, is that a good proof of why sine x over x has a limit of 1 as x goes to 0? Well, it's okay from the graphical evidence. If you want a better or a more sort of algebraic proof, you can head to the Khan Academy, and I'll put a link at the end of the video. So we're going to take this as true from graphical evidence. There's the graph again, even though this has a hole right here. All right, to the matter at hand. Limits with algebra. So graphs are extremely helpful when you evaluate limits, but you have to have a good graph, and that can be difficult. Maybe less so with technology, but analytically, it can be tough to get a really nice graph. So limits can be considered algebraically too. Whenever possible, if you want to find a limit, you just sub into the function. So if I want the limit on this as x goes to 3, I already know that that's just a vanilla polynomial. It exists everywhere. It's got no weird jumps in it. I can just sub in. Okay, so I'm going to sub in 3. And so I'll get 3 squared minus 2 times 3 minus 3. Oh my gosh, I would get 0. Let's take a look at the graph. You can see right on the graph that it really does have a limit of 0 as x goes to 3. In fact, that's one of its x-intercepts, and the graph does exist there. That was easy. So sub in, that'll find you your limits. But sometimes you can't sub in. And the question is, do we give up or do we try something else? So explain why substitution can't be used to evaluate each limit. If possible, evaluate anyway. A graph may help. So in this one over here, this is, well, first of all, let's try and sub in. We'd get square root of negative 3 minus 2, or root negative 5, which is undefined in the real number system, and we're going to work in the real number system. If I graphed this thing, I already know that a square root graph kind of looks like this, and it's been moved 2 to the right. So it's really silly to ask about, what's its limit back here? It doesn't exist around x equals negative 3. So it doesn't exist in the neighborhood of x minus 3. So it's silly to ask about a limit there. Okay, so we can't find this limit. We could say this limit does not exist. Now let's try the next one. If I put in 2 into this, what will I get? I'll get 2 minus 2 all over 2 squared minus 4. I'll get 0 over 0, which is not 0. That is still undefined. And I don't really know what's going on, so let's take a look at the graph. That might help us out more. And here's the graph. It looks like it has a vertical asymptote at x equals negative 2. But if I think about what's happening around 2, it does appear to be approaching something from the right and something from the left. Now, what y value do you think it's going towards? It looks 0.251 from the left, 0.24 something from the right, but when I get right on 2, it's a hole. I think it's pretty safe to say that the limit's going to be 0.25 or a quarter. Let's change the scale so that maybe we can see what's going on. Ah, there it is. It helps us see it right now. As x goes to 2, it looks like it's going right up to that 5th block, and each block is worth 0.05. So 0.25 seems like the limit. So we can say the answer here is 0.25 from the graph. But it requires an amazing graph to be able to see that. Maybe the graph isn't even that helpful. So here's the thing that you can do with a limit, and this is the special thing that limits give us in algebra. As soon as you saw that x squared minus 4 on the bottom, you probably thought, oh, I could factor that, right? I could factor it as a difference of squares. And once we do that, we can divide out the x minus 2. And the reason that we can do that is because the limit as x goes to 2 is not saying that x is 2. It's saying x is really close to 2. It's closing in on 2. So you're not actually dividing out 0 over 0. You're just dividing out really close to 0 over 0. And then you've got a simplified expression. And in this one, you can't sub in 2. You can go 1 over 2 plus 2. Oh my gosh, which gives us a quarter, which is the same thing we got from the graph. So substitution doesn't always work, but there are some other algebraic tricks we can exploit, and we should try these when we get an indeterminate form. And by indeterminate form, for now what I mean is if you get 0 over 0 or infinity over infinity. So if you get those answers of 0 over 0 or infinity over infinity, there's still hope that there might be a limit. And you can probably find it, or hopefully find it, by either factoring, by multiplying by conjugates, and you would do that to deal with radicals, just like you did in 521b or in rationalizing denominators. Sometimes here we'll be rationalizing numerators instead. Dealing with nested fractions or fractions within fractions. Maybe combining fractions. Or we might end up using this fact that the lim as x goes to 0 of sine x over x is 1. And that also means that the lim as x goes to 0 of sine 2x over 2x, as long as they're the same thing, is also going to be 1. And the lim as x goes to 0 of sine 3x over 3x is also going to be 0, or is also going to be 1, rather. As long as they're the same on top and bottom, you get the same result. So there are 6 for us to try here. In every single one, though, we're going to try to substitute first, because if we can substitute, that is by far the easiest way to evaluate these. All right, let's try and substitute. That'll give me 2 squared plus 3 times 2 minus 10 all over 2 minus 2, or 0 over 0. Substitution did not work, but we got one of these indeterminate forms, like 0 over 0 or infinity over infinity. There's hope. Maybe we can find a limit. Okay. So I think about my toolkit. Right here, it's really, really fishy that that top is factorable, and that was the first thing it told me to try. I've got 5 techniques. Factoring's the first. So the top factors as x plus 5, x minus 2. And you can see right now, we can divide out factors of x minus 2 on top and bottom. And we can do that because x is not 2. X is just really close to 2. And we get rid of our whole problem, and now we sub. So we can put in 2 now that our problems are gone for x, and the limit's dropped once you sub. And we get this limit of 7. And we could take a look at this graph and figure out whether that's true. But it's true here that we kind of get to have it both ways around with a limit. We get to exploit these helpful properties by saying, x isn't 2, x is just real close to 2. And then, once we get rid of our problem, we can say, well, x is basically 2. That's algebraically how we deal with a limit where we can't just sub in. Let's take a look at the graph. There's the graph. The lim as x goes to 2. I mean, clearly it looks like it's going towards 7. And you might say, oh, that's just a line. That's weird. But it is a line with a hole in it. Okay, if I can get, there you go. It just briefly said it, undefined. There's the hole. The limit is 7. And we found that limit algebraically. Let's try another one. I've got lim as x goes to 4 on this. So again, what I'm going to try first is just subbing in. So if I put in 4, I'll get 4 minus 4 all over the square root of 4 minus 2. In other words, I'll get 0 over 0. No, I can't sub in. But it was worth a shot. But I got an indeterminate form, so I'm going to try something. Whenever you have radicals with binomials, it's worth trying conjugates. Okay, so what I'm going to do here is I'm going to multiply the top and bottom by root x plus 2. Brackets around everything. And let's see what we get. I'll still have a limit. And on top, I'm going to leave it just in its unexpanded form. And on the bottom, conjugates are going to do what conjugates are going to do. Root x times root x, well, that's going to be just x. Okay, because it would be the square root of x squared. And we're dealing with positive numbers, so we don't have to worry about absolute values. So that's going to give us x. This will give us plus 2 root x minus 2 root x, so those are gone. And minus 4. And now you can see where the magic can happen. We can divide some stuff out. X minus 4s can divide out. And hopefully that gets rid of our problem. And we've got it in this sort of simplified form where the problem's gone. Now let's try subbing again. Now try subbing 4 for x. And as soon as you sub, you're evaluating the limit. So you drop the limit notation, and that will give us 2 plus 2, or 4. I guarantee you, if you look at the graph of this, as x goes towards 4, y will also go towards 4, even though there may be some kind of hole there. Next one. This one has 2 variables in it, which is annoying. But when I try and sub this in, let's see what happens. It's probably going to have an answer that involves x's, so I'll have 3 over x plus 0 minus 3 over x. So far, so good, because it doesn't matter whether it doesn't say x is going to 0. And then if I sub in the bottom, I'd have, oh geez, I'd have a 0. This whole thing is undefined. So it makes me think, I don't know exactly what is going to happen. And the top would also be a 0 in this case. So let's deal with these fractions. And I've shown you a way that I like to deal with nested fractions. You can do it a different way if you want. I like to find the lowest common denominator of the little fractions. And then I'm just going to times the top and bottom of the whole fraction by x plus h. And this is all in the hopes that I can get rid of that problem and evaluate my limit, or get an expression. So I will multiply this through, and in that case the x plus h's will divide out. So I'll just be left with 3 times x. I'm going to keep my limit because I haven't actually subbed in 0 for x, or for h rather. So 3 times x. Okay, so again, where's that coming from? That's coming from this multiplication, and the x plus h's would divide out, so I'd have 3 times x. The other one, well, I'll do this multiplication, and the x's will divide out. So I'll have negative 3 times x plus h. Minus 3, bracket x plus h. I'm playing it really careful here. I'm not multiplying out anything. On the bottom, I would have x by h by x plus h. There's no point in multiplying anything out on the bottom because I'm hoping to divide something out in the end. So factored form is better. Up top, I'd have 3x minus 3x minus 3h all over x by h by x plus h. And at this point, people are going to do ridiculous stuff. They'll divide out this x and this x and this h and say we've done something reasonable. That's not true cancellation. You need to have things all simplified and factored out, and then you can divide out stuff that's common on top and on bottom. So the top here means negative 3 times h. The bottom means x times h times bracket x plus h. Here's what can truly divide out, is the h's. And those particular h's. So I'm left with negative 3 over x by x plus h. You might say at this point, well, that's no better because we still have an h on the bottom. But is it the kind of h that causes you a problem? Let's try to sub. Try to sub 0 for h. Okay, so that will give us negative 3 over x by x plus 0. Or negative 3 over x by x. Or negative 3 over x squared. That's what this limit's going to be. It's not a number yet because we haven't subbed in an x value. It's going to be defined as long as we don't use x values of 0. But we were able to get rid of our issue that gave us 0 over 0 to start with and at least give us an expression. This idea of ending up with an expression is going to follow us through later on. Most of the time for now we're going to find limits that are numbers, but eventually we'll go towards expressions. Here's another one. And here I'm going to have 1 over 0 minus 2 over 0 when I put them together, or undefined minus undefined, which is another sneaky way of writing an indeterminate form. If you see two fractions, try and turn them into one fraction, and that's probably what we would assume we'd be doing anyways. And the way to do that is to create a common denominator. And the way to find a common denominator is probably to factor the bottom. So instead of writing it as x squared minus 1, I'm going to write the bottom as x plus 1 by x minus 1. Okay. So think about if you were doing like 1/2 plus, I don't know, 5/6. You'd need a common denominator. It would be easier to find that common denominator if you wrote 5/6 as 2 times 3. And you go, oh man, I need to times this one by 3 over 3. And then you'd get 3/6 plus 5/6, and that would help you out. That would give you 8/6, which you could reduce in the end. It's the same idea here. We want to get a common denominator. We can see that both of those denominators have an x minus 1 bracket. What is the first one lacking? Well, it's lacking an x plus 1. So we think about all these things as being in brackets when we multiply them through. And that will give me the lim as x goes to 1 of x plus 1 all over x minus 1, x plus 1, minus 2 over x plus 1, x minus 1. Doesn't matter what order we write them. At this point, we have a common denominator. Right? And somebody might want to do this, but that just puts you back where you started. So now that we've got a common denominator, let's go ahead and write them as a single fraction. Lim as x goes to 1 of, it'll be x plus 1 minus 2 all over, doesn't matter which order you write these in, x plus 1, x minus 1. It's still no good here. If I put in 1, I still have a problem in the bottom of division by 0. Here we go. So the top simplifies to x minus 1. On the bottom we have x plus 1, x minus 1. And here is where true cancellation can happen. And hopefully that means that we've gotten rid of our problem. So this whole thing simplifies to 1 over x plus 1 sub x equals 1 now to actually evaluate the limit. 1 over 1 plus 1, or 1/2. I guarantee you, if you look at the graph of this, as x goes towards 1, the y value will be approaching 1/2. And all we did was create a common denominator and just followed the algebra through, got it as simple as possible. Basically, in limit land, you don't have to worry about restrictions because you're never actually at that x value. You're just approaching it. And then eventually, once all your problems are gone, you can sub in. Very sneaky. Limit as x goes to 0 of sine 3x over x. So again, we're looking at all these ways of interpreting or maybe exploiting properties. And here's the one that's probably going to spring to mind. Lim as x goes to 0 of sine x over x is 1. And we said, oh, that means the same thing if you have sine 2x over 2x or sine 3x over 3x. So in this question, if I had to make like a wish list, I'd say, I wish this said lim as x goes to 0, not of sine 3x over x, but of sine 3x over 3x. Okay, there's nothing you can do about this 3x. It's stuck within the sign. You can't mess with it. But if it said that, then you'd know, oh, that limit is just 1. And here's the thing. You can build it. You want it to say 3x on the bottom? Bam, go for it. Times the bottom by 3. But if you times the bottom by 3, you have to times the top by 3 as well. Well, what's that going to give us? On the top, that will give us 3 sine 3x. Okay, because it's not like this 3 multiplies by that. The 3 becomes sort of a coefficient in front, or it affects the amplitude of the graph. And then we'd have 3x. And so that means really this is just 3 times sine 3x over 3x. There's no point at which you can sub in. And if we had tried to sub in here, we'd get 0 over 0. But there is a point at which you can evaluate. As x goes to 0, this 3 becomes a 3. As x goes to 0, this part here becomes 1. And that's because of this property. And we showed it at the start of the lesson, and we put it in our sort of notes of things we can try. This is going to be 3. Let's double check. You can see it right there. As x goes to 0, this has a limit that is going to be 3. Anytime they're trig-y, you're probably going to want to think about that sine x over x business. So if I see a tangent here, I'd be inclined to think of this. Well, first of all, I might just split it up. It means tan x times 1 over x. Maybe that'll help me. Otherwise, I'm going to have nested fractions. I'm not too happy about that. Tangent, we know, is just sine over cosine times 1 over x. And you can rearrange that. What you want to build sine x over x. Because we know this limit. Lim as x goes to 0 of sine x over x is 1. Okay. So let's group the sine x with the x. And the cos x will be the leftovers. Still means the same thing. I've just rearranged where I saw the multiplication. That's the lim as x goes to 0. And now we're either going to evaluate slash sub. So evaluate. Can't really sub in 0 in the first one, but we know as x goes to 0, sine x over x becomes 1. This one here becomes 1 over the cosine of 0. And the cosine of 0 is not 0. You can double check it in your calculator. You can think about the unit circle. Okay. The cosine of 0 is 1. So this is also going to give us a limit of 1, which we can also verify graphically. There you see it. Limit of 1 as x goes to 0. Neat looking graph too. If we nitpick, we can also have some other situations that we can find limits for, or maybe attempt to find limits for, that involve piecewise functions and involve absolute values. If you can make a graph when stuff is weird, probably so much the better. Okay, so over here, if I put in 0, I'm going to get 0 over 0. That's not great. So maybe I can generate this graph. And maybe I'll think about putting in the number 1 into this graph, or into this function. I'd get 1 over 1. The y value will be 1. If I put 2 in, I'd get absolute value of 2 over 2, which is still 1. If I put in 10, I'd get absolute value of 10 over 10. And the absolute value of 10 is just 10, so you'd still just get 1. If I put in 0.01, I'm still just going to get 1. So it looks like this graph is just, y is always 1 here. Now, I don't know what happens exactly when x is 0. The graph is not defined there. What if we put in negative numbers? What would we get? Well, I get absolute value of -1 all over -1, which would be 1 over -1. Oh dear. So here at -1, I'd have this point. If I did it at -2, I'd get absolute value of -2 over -2, which would be 2 over -2. Still give me -1. So it would be right here. And really, with any negative number that I use, I'm still going to get -1. So I'm going to end up with a graph that looks like this, just from table of values. If I were looking for the left-hand limit, okay, as x goes to 0 on this function, it would be -1. If I were looking for the right-hand limit on this function, well, then it would be +1. And since they are not equal to each other, or if you did this with your fingers wouldn't touch, the overall limit does not exist. It doesn't not exist because the function is not defined there. It doesn't exist because the limits from either side are different. The last nitpicky thing we'll deal with in this video is limit rules. And limit rules are actually pretty intuitive. If you had to make them up yourself, you'd probably make them exactly as they are. The limit of a constant is a constant. So the limit as x goes to whatever on the number 3 is 3. 3 is always 3, no matter what. This one here says the limit of a sum of functions can be split apart in the sum of those limits, which may or may not be helpful to us eventually. If you have multiplication, well, you can split that apart. If you have a constant, you can pop a constant out front, and this all seems very abstract right now. If you're looking for the limit of a fraction, well, you could do the limit of the top and the limit of the bottom, as long as that doesn't cause you undue issues. And if you have a limit of a power, well, you could pop that power outside. So in other words, you could do the limit of the simpler part and then apply the power, provided the statement exists and doesn't cause us to do weird stuff like take even roots of negatives. I'll show you what that means in a couple of little sort of logic puzzly questions. So let's suppose we've got two functions that we're never going to know what their equations are. All that we know is that on f of x, as x goes to 2, y goes to -8. And on g of x, as x goes to 2, y goes to 1. So the question is, what is the limit as x goes to 2 on f of x plus 7? Now, there are a lot of ways to think about this. F of x plus 7 is just the original one moved up 7. So intuitively, its y value is just going to go up 7. So now it'll be -1. You might also just say, I think that that's -8. This thing here, I'm going to call it -8 plus 7, give you -1, and you'll be right. Now, I think that's probably glossing over what the limits are actually doing here. If you want to be really formal about it, our second law up here said that if you have the limit of a sum, you can split it apart. Okay, so the lim as x goes to 2 of f of x, and then do the lim as x goes to 2 on 7. And we know the lim as x goes to 2 on f of x is -8. And from the first rule, the limit of a constant is a constant. So we'd go plus 7. And we just get -1 in the end. If you're inclined to do that with way less work and just say, I think it's -1, again, limit rules are, or limit laws are intuitive enough or close enough to what we would make them up to be if we invented them independently, that you'll probably be right. The next one says, well, what if we have limit of 3 times g of x? Again, we know about function transformations. A 3 in front of a function means a vertical stretch by a factor of 3. So if the y value was going to be 1, or was approaching 1, then now it'll be 3 times its tall. It'll be approaching 3. The real thing that's happening here, though, is that you can pop a constant out front in limit rules. And that would be the fourth limit law here, where it says kf of x. Okay, we're using a g, but that means we'd have 3 times, and we know the limit as x goes to 2 on g of x is 3. We never have a graph to check these with, though. We never know what f and g actually are as functions. And then that very last one was saying, well, what if you have powers? You can do the limit and then apply the power if you want. So the limit as x goes to 2 on f of x is negative 8. So it would be negative 8 to the 2/3, okay, which is the cube root of negative 8. That's negative 2. Squared is 4. And again, if you just said, that looks like negative 8, and I'll apply those powers, you'll probably be right. There's some practice questions from an older textbook called Calculus and Advanced Functions that deal with mostly just applying some limits and maybe doing some factoring and nested fractions and the like. And there's also some ones from our textbook, which is the Finney 4th edition. It only gives odd answers, so they're the relevant even answers. In the next video, we'll deal with the rest of this section. I hope this has been helpful. Good luck with the material, folks, and take care.